Hi class, Mr. Morris. We're introducing a topic today called elementary reactions. It's kind of a preview of something we're going to be talking about a little bit more later. So one of the major reasons that we're studying kinetics is it's used to use measurements of the macroscopic properties of a system, so things like rate of change in concentration, to discover the sequence of events that take place at the molecular level to make the reaction happen. The molecular description is what we call the reaction mechanism. Okay, it describes how the individual atoms, ions, or molecules interact to form particular products. Essentially, it's the stepwise changes that are collectively called the reaction mechanism. We discussed that more in Unit 5.7, which is coming up probably next class period. We'll look at an example here. An internal combustion engine, we have isooctane reacting with oxygen to produce carbon dioxide and water. So here's our overall chemical reaction. You're used to seeing regular chemical equations written out like this. So what this reaction's telling us is that we would have 25 oxygen molecules reacting with 2 isooctane molecules, this molecule right here. And that's going to they all have to collide at exactly the right time, the same time, in exactly the right way to turn into 16 carbon dioxide molecules and 18 water molecules. That is very, very, very unlikely to actually happen. Okay, it's more likely that we're going to have, and that's what we're saying down here, it's more likely that we're going to have a complex series of reactions that takes place in a stepwise fashion. Each individual reaction, which is called an elementary reaction, involves 2 or sometimes 3 atoms or molecules or ions. It's actually extremely rare to have a step that involves 3 molecules. An elementary reaction is a chemical reaction in which one or more chemical species react directly to form products in a single reaction step with a single transition state. So in practice, we can assume that a reaction is elementary if no reaction intermediates have been detected or need to be postulated in order to make the reaction make sense. Sometimes an apparently elementary reaction could be a stepwise reaction. So there could be a complicated sequence of events even though it looks like it would be pretty simple and straightforward reaction. So here's the difference. Basically, we've got a few differences between elementary reactions and complex reactions. Elementary reactions are single step. Complex reactions, multi-step reactions made of a series of elementary reactions. So it's a combination of multiple elementary steps. The overall chemical equation represents the actual changes taking place at the molecular level in an elementary reaction. But in the complex reaction, the overall chemical equation just summarizes the overall change involved, not the step-by-step process that takes place to make it happen. The rate law can be written. Now this is a key difference. I would highlight this if nothing else. I would note these two sections. Just make sure that you're aware of this. In an elementary reaction, the rate law can be written based on the elementary chemical equation. The order for the reaction, the reactants, is equal to the coefficient in the balanced elementary equation. That is not true for a complex reaction. If it's not an elementary reaction, we can't make that assumption. We have to use experimental data to find it. Just like we've been saying, you have to use an experiment for most chemical reactions. But if you know what the elementary reaction is, you can deduce it. This is how. Your rate law is rate equals K times the concentration of A to the coefficient's power times the concentration of B to the coefficient of B power. That is if and only if it's an elementary reaction. But for most reactions, a complex reaction, we will write our rate law as k times a to the m times b to the n, where m and n are not necessarily the same as the coefficients. So it's not necessarily the coefficient of the reaction with an overall complex reaction. All right, we've got a couple different diagrams here. You've got your reactants and your products. We're going to go through a set of notes where we evaluate a lot of graphs that look like this, but we want to get the general idea. This is an elementary reaction. It's one step. You just have one transition state. This is a two-step reaction. The energy has to increase to make it happen, and then we have this valley, which is where the intermediate is, and then we have a second transition state going to the products. Transition state is kind of an in-between state that we'll go into more detail on in a later video. Okay, so this is a sample reaction coordinate of an elementary reaction, one transition state, and there's no intermediate. The intermediate is the valley, the transition state is the hill, so to speak. Elementary steps cannot be broken down into simpler reactions. This is a reaction coordinate of a complex reaction that has two transition states. It involves an intermediate, again the valley, and multiple transition states. We have two hills in this case. That's two transition states. A complex reaction can be explained in terms of multiple elementary steps. This is our first step. This is our second elementary step. All right, we have some different types of elementary steps. Most reactions are complex. They have two or more elementary steps, so the rate law cannot be deduced from the coefficients of the overall reaction. I'm reiterating that. But we can deduce the rate law from the coefficients of an elementary reaction. So we need to know a couple things in order to do that. The number of molecules involved in the elementary reaction is called the molecularity. The molecularity is equal to the number of reactant molecules. Let me just write that down. The number of reactant molecules. It is considered unimolecular, uni means one, unimolecular if there's only one reactant involved in the elementary step. And the rate law for a unimolecular reaction step would be K times the concentration of A. We have a couple different examples of bimolecular. You could have two identical reactants in which our rate law would be rate equals K times the concentration of A times the concentration of A, or an easier way of writing that is K squared. And then if I have two different reactant molecules in an elementary step, then it would be rate equals K times the concentration of A times the concentration of B. And then if we have some, these are extremely rare, by the way, termolecular elementary steps. They're rare, but they do happen. This example would be K times the concentration of A times the concentration of A times the concentration of A, or just Ka cubed. This one would be the concentration of K times the concentration of A. We've got two of them, so I'm going to say squared times the concentration of B. And of course, another example is if they're all three different molecules, then it would be rate equals K times the concentration of A times the concentration of B times the concentration of C. But the coefficients guide us in determining what the power is going to be, or what the order is of that elementary reaction. Okay, we've got some examples over here. This is an example of a unimolecular step. There's only one reactant molecule. This one's a bimolecular reactant step. We've got two NOCl molecules, so it would be concentration of NOCl squared. This is another bimolecular. It would be concentration of CO times the concentration of NO in our rate law. We don't have an example for this termolecular step. It's pretty rare. For this one, our example is 2NO plus O2, so it would be the rate equals K times the concentration of NO squared times the concentration of O2. And then finally, the last example, rate equals K times the concentration of H times the concentration of O2 times the concentration of AR. That's it for elementary reaction notes. We're going to continue notes with section 5.5.